So in the last couple of lessons, we've learned about what a linear function looks like, what a quadratic function looks like, and what an exponential function looks like, and we've looked at real-world examples of that. For this next lesson, we're going to put it all together and look at different data patterns and decide whether they fit a linear, quadratic, or exponential model. So to get started, I'm just going to put up some graphs and I will call on students to let me know what type of pattern this is. Is it linear, quadratic, or exponential? Here's the first graph. I'll give you all some time to figure out what pattern it is. All right, so some of you have figured out that this is an exponential curve, and then I'll just go over quickly the best way of describing why it's exponential. So with an exponential pattern, it's best to describe it in terms of end behavior. So what you notice here on the left is that as x gets closer and closer to negative infinity, y gets closer and closer to a value, which is 0. So as x goes to negative infinity, y goes to 0. And then on the other side, as x gets closer and closer to positive infinity, y also gets closer and closer to positive infinity. So this end behavior is different. So this is the best way of understanding how exponential graphs are different than quadratic. If you have quadratic, shown by this drawing in red, as x goes to negative infinity, y also goes to positive infinity, and x goes to positive infinity, y also goes to positive infinity. All right, for this one, I think you all know this one. It's a linear growth, so that means it's a line. And behavior. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y also goes to positive infinity. And then the important thing to notice about linear growth is that as if x goes up by 1, y also goes up by 1. Anywhere along the graph, it's always going to be the same. So slope is always the same anywhere on the graph. What is this pattern? And then this is another one we've seen a lot, and this one is a quadratic pattern. And a good way to explain this, what's going on here algebraically, is that what we saw with the linear function is that if it's just a straight line, slope is always the same, right? But then with this one, with this quadratic function, what you notice is the slope is always changing. So what we're going to do in this lesson is just look at it algebraically, look at the numbers in a quadratic pattern and see what happens when the slope is changing in a quadratic pattern. So here's a little illustration of the difference between linear and quadratic. If you're driving and you're always going on at the same speed, that is called linear because the rate of change is not changing as you go along. So this is what it's like when you're driving in your car at the same speed. That's a linear pattern. And then, but then if you're in a really fast car that's going from 0 to 60 in 6 seconds, this is quadratic pattern because the rate of change is changing. You're going from 0 miles an hour to 60 miles an hour, and so this is what that's like. So that's one way of looking at it, and then we're going to look at it, the difference between linear and quadratic, just by looking at the numbers now. So we're going to go over two main techniques for identifying linear versus quadratic versus exponential patterns. And the first one is going to be this technique of finding the first difference and then finding the second difference. So we'll just do that with this here. So this is y equals x squared. We're going to find the first difference. Well, first we're going to plot the points. So if x is 0, y is 0. When x is 1, 1, 1 squared is 1. So we're going to figure out the first difference. So that's 1. Difference between 1 and 4 is 3. So this is sort of like finding the slope. First difference here is 7. So this shows how the slope is changing as x gets bigger. So if it was a linear function, then this first difference would always be the same. But it isn't, so that means the slope is changing, so that gives us a clue that it's actually quadratic. And in a quadratic function, this change in slope, the second difference, will always be the same. So this is why we calculate the second difference. All right, so the second difference between 1 and 3 is 2. The second difference between 3 and 5, 2. Second difference between 5 and 7, 2. So this is a characteristic of quadratic patterns. So what you could do is, if you just had this information, you could do regression formula, and it would give you this as the regression. And so what's going to happen is we're going to be given data for real life situations where it's going to, and we're going to say, oh, does this fit a linear pattern, or is it more like a quadratic here where the slopes are changing in a uniform way, or is it an exponential? So this is a way of identifying quadratic patterns. Now I'm going to show for you the second technique that we're going to use to identify exponential patterns, and that is the ratio. So what we're going to do is look at this function we have right here, y equals 2 to the x. So this is an exponential pattern. Let's plot some points. 2 to the third is 8. 1x is 4. 2 to the fourth is 16. And this one, we don't look at the difference in the second difference. We look at the ratio from one to another, right? So the ratio of this one is 1/2. The ratio of these two terms is 2 over 4. The ratio of these two terms, 4 over 8. The ratio of these two terms is 8 over 16. So for all of these, the ratio is 1/2. So if a function is going to follow the exponential pattern, these ratios will always be basically close to the same value. So here we go. Our task now is to be able to tell if this is linear, quadratic, or exponential, not by looking at the graph, but just by looking at the numbers. So here we have a data set here. And what we can do is just, what we said before was that we know that linear graphs are characterized by the slope doesn't, you know a graph is linear if the slope doesn't change. And you know a graph is quadratic if the slope always changes by the same amount. And so if this is quadratic, then this second difference is always going to be the same number all the way down. Let's see what the first difference is. So the difference between 3 and 1/5, 3 and 1.5 is 1.5, and then let's see, this is going to be 3, right? Because it starts off at 0, 0. Difference between 1.5 and 1 is 0.5. This again is 0.5, and then this is 1.5, and then this difference is 2.5, and then this difference is 3.5. Now we can analyze the second difference. So the difference between 1.5 and 0.5 is 1. Difference between 0.5, so this is, negative. These are all negative values. 0.5 and negative 0.5 is also 1. Difference between 0.5 and negative 1.5 is also 1. So what this does is the difference between the slope. So basically what we're saying here is that the characteristic of a quadratic function is that the second difference will always be an equal amount. And that's something you'll always see with quadratic functions. So if we actually graph this, it's going to look like this. 0, and then this is going to be 0.5, and then this is going to be 1. Then it goes up again. And just because the second difference is always the same, we can tell that this is going to be a quadratic function with a characteristic quadratic parabolic shape. So here's another real-world situation, and what our task here is to decide if this is going to follow a linear or a quadratic or a exponential pattern. So we think it may be quadratic because the data comes in at even increments, and then you notice that the population doesn't grow in a linear fashion. So what we're going to do is just calculate the first difference and the second difference, and then we're going to see if we can use a quadratic model to predict what will happen with the population of whooping cranes. So if this data follows a quadratic pattern, that means we could create a quadratic function and then predict what the population will be in 2020 and then in 2030. So let's get the first differences. So here this is 12, this is -1, this is 23, this is 20, and then it starts going up, so this is 70, and then this is 104. Now we're going to get the second difference for this. So if it's quadratic, then the second difference should be about even, right? So let's see, here the second difference is 13, and then here the second difference is 24, here the second difference is 3, here it's 50. So you see it's just all over the place. So we can say that this is not quadratic. So we think it's probably going to be exponential. So in order the test for figuring out if it's exponential is to figure out the ratio. So if you remember with exponential patterns, it always goes like 2, 4, 8, 16. So it's always like being going up by some power. So is that happening here? So to figure that out, we take the ratio. Instead of taking the second difference, we get the ratio. So here, let's figure out the ratio. 34 over 22. And then here we're going to figure out the ratio. 33 over 34. Here I finished calculating all the ratios. And what we notice is that the exponent, so 22 to the power of 1.55 is 34, 34 to the power of 0.97 is 33, and so on. And then you see that that ratio is about the same. So for this one, you can use an exponential model for this one. So the procedure is you figure out the first difference. If you think it's linear, then all of these will go up by a linear amount, but they don't. So you think, okay, maybe it's quadratic. So then you calculate the second difference, and then you notice that the second differences aren't the same. So you say, okay, this is not quadratic. And then you think, okay, maybe it's exponential. And then you calculate the ratio of, successive data points. So when we did that, we found we got these numbers, and those numbers were close enough that we could say, yes, this fits the exponential model. And so the next thing we would do is do regression, which you know how to do, and we'll go over that tomorrow.